Hello everyone, today we're going to be looking at the friedel-craft reactions, specifically alkylation and acylation. This first one here that we're looking at is alkylation, and that's just adding an alkyl group in a similar fashion to what we've seen with the nitration and the sulfonation and the halogenation, same sort of fashion, having that aromatic compound but adding an alkyl group. The reagents we have to use is some sort of alkyl halide, primary, secondary, preferred. And then using the catalyst aluminum trichloride, that is a helpful reagent. And you can see I have an example down there, another example. It adds that big clunky group to that benzene ring. So let us get into the mechanism, shall we? Okie dokie, let's start the mechanism here. We're going to start with our alkyl halide. Remember that R is just any alkyl group, assuming that this is primary or secondary, to make this reaction occur to any appreciable amount. So it starts with the halogen, the alkyl halide's halogen, reaching out, and we'll just use some fun colors today. One of the lone pairs is going to reach out to the aluminum and form this compound here. All right, what charge has changed? Well, aluminum, of course, has a negative charge. It gained some electrons. And the chlorine here has a positive charge because it has two bonds. Well, we know chlorine would rather die than have a positive charge. So the R group is going to bear the positive charge because it's just an alkyl group, right? It's carbon. Carbon is not as electronegative as, say, chlorine, so it's happier taking a positive charge. So this is the first step of the mechanism here. Alkyl halide's halogen reaches out to the aluminum trichloride, and then that's going to form aluminum tetrachloride with that alkyl group still attached, and then we really form aluminum tetrachloride, and we leave the carbon R group carbocation. So what happens next? Well, let's grab our aromatic compound. Today I'm feeling benzene should be purple, so we're going to draw benzene as purple. You know what? To make it even more fun, we're going to add all the bonds as being different colors. Because, ew. Yellow is such an... Oh my, I can't draw straight lines. My goodness, guys. Here's our little nice looking benzene ring. Looks like a little playful little thing. The R group electrophile, wherever that positive charge is, could rearrange. We will see that as a problem in a minute. That R group is going to be attacked by these pi electrons on the aromatic compound, giving us this species here, which I'll just draw real quick. Oh, that was terrible. That's a lot better. Okay. Whew. And then R group coming off the side. We're going to draw in a hydrogen. We'll see why in just a moment here. And we're going to put a positive charge on this carbon here. A positive charge right in here. All right, so we see a positive charge. Hopefully you see the pattern here with past reactions. We need to come in with something to restore aromaticity. In this case, we're going to go with our catalyst that we made back here, the aluminum tetrachloride. So let's draw that in, shall we? Aluminum has a negative charge here, so chlorine isn't hating the idea of just picking up the hydrogen and eliminating into a pi bond here. Doesn't hate the idea. And we get our catalyst back, and we're also going to get restored aromaticity. Remember, this is the sigma complex here. That's important. I keep forgetting to point that out. Sigma complex. It's important to know when you form it. Almost all these reactions form one. And we like to see it because it's highly resonance stabilized, helps the reaction go forwards. So let's just draw in our R group, and then I'll show that we restored our catalyst here. So let's summarize the mechanism, and then I want to get into a couple little niche topics about alkylation before we get into acylation. So remember, we have our alkyl halide, reaches out to the aluminum trichloride, forms this compound here, right, this compound. And then that R group is going to bear the positive charge instead of chlorine, because chlorine doesn't really like to do that. Then that R group acts as an electrophile to the aromatic compound. We're going to attach, do an elimination with that aluminum tetrachloride that we had, and then make our aromatic compound with that R group attached, and restore our catalyst here. So now let's get into a couple issues that might occur with alkylation. Alrighty, everyone. I want to go over a couple problems that might happen with friedel-craft's alkylation. We're going to first look at polyalkylation. Polyalkylation is just like if we remember polymerizing many subunits together. Poly, many, alkylation, alkylation. So we're just going to polyalkylate or alkylate many times. This will happen because this R group is going to be what's called an activating group, and we will get to that in the lateral part of this course here. So we have that attached R group, right, and it's going to activate, add electron density to that aromatic compound, make it even more reactive than just a base aromatic. And as a result, we get a mixture of products here like this or this here, and that's not what we want. Moving on, we have rearrangements. Let me just bring this down a little bit. We could have a rearrangement of sorts, right? I just want to go through it here. If you were to predict the products, how would you predict them? The correct product is a little bit different than what we'd expect. We get an isopropyl group instead of what we might have assumed, like this, right? Some of you may have guessed this here would be, no, we don't get this. Mallow, bad, mallow. He's angry because you picked the wrong answer. Just kidding, it's okay to get the wrong answer. The reason that we get the isopropyl group instead of this linear propyl group is, we'll show you here. Let's just take our propyl halide, and we're going to react it with that aluminum trichloride. So we have just a lone pair hanging out here, bonds to that, right? We've seen this before. All right, chlorine has a positive charge, and chlorine takes the electrons there, and we're left with this. Now, hopefully you can see it here. We have a primary carbocation, and if we remember methyl and hydride shifts, we'll know that, okay, we can make a more stable carbocation if we were to, say, do a hydride shift. So that's exactly what happens. This hydrogen basically swaps places, and we get this. And when that attacks the aromatic compound, that's going to make a propyl group, or an isopropyl group, I should say. Right? So aromatic here, it's going to attach like this, right? That V shape. So that is our second problem of rearrangements. Got to keep those in mind. All right, now I want to look at Friedel-Craft's acylation here. So we have an aryl halide, we have aryl chloride, right? So that's just, you can see the reagent here. We have a chlorine, and then we have a carbon here, a double bonded oxygen, and then an R group coming off. That could be whatever. And in the presence of the same catalyst, the aluminum trichloride, it's going to attach like this here, where we lose the chlorine and we gain this oxygen ketone group next to the aromatic in that R group. So let's get into the mechanism now. Alrighty, let's get into the mechanism here. It starts with our reagent, the acyl halide. specifically acyl chloride here, and we have aluminum trichloride, and all that happens is that chlorine is going to reach out much like the alkylation step and reach out and bind to that aluminum. And I'm drawing in blood red. Let's go back to the dull black. Why don't we? Chlorine, and then that aluminum binds as such. You get a negative charge of that aluminum and a positive charge at the chlorine. Don't forget, Corbin, your oxygen. Okay. Well, we know that chlorine there, it's not particularly going to like that positive charge, so it's just going to steal the sigma bond electrons from this carbon chlorine bond here, and we're going to get this compound here. I'm going to elaborate everything because it's quite important. Hopefully you can see some resonance here maybe. And it might not be inherently obvious that there's resonance, but let's take a look. Let's try and draw resonance structures here. We know that chlorine has the positive charge and this oxygen here is neutral, so if we were to go like that, we might get this compound here. And you're like, well, this probably isn't a major resonance contributor, and you would be wrong. But why are you wrong? Let's look. Oxygen has a positive charge. It doesn't really like that, right? But notice how we have more bonds here, and that because we have more bonds, it lowers the energy of the molecule. So this is our major resonance contributor here, even though oxygen has that positive charge and doesn't preferably really like it that much, right? But it still happens. All right, so doing this, we're going to have our aromatic species here come in with some pi electrons and attack the carbon, right? And that's going to arrow push some electrons this way onto the oxygen, stabilizing it. We're going to get this compound here. Let me just come over a little bit. We're going to have this group and this R group. Again, we're going to draw the hydrogen. No more surprises here because we know that probably going to see some sort of elimination. And you'd be correct. Let's use some fun colors now because I'm getting bored of these dull black colors. So we have that positive charge here. Remember that we made this reagent. We'll draw it in orange because I think orange is a really beautiful color, and anyone who disagrees is sadly mistaken. And I'll just draw the charge in red. So this compound has a negative charge. So what's going to happen, so we can neutralize both the negative and the positive charges, elimination by making an acid. And our final compound is going to look as such. So we successfully attached a ketone group, C double bond O group, to an aromatic compound. So let's go back through the mechanism one more time and let's review. Okay, so we had this compound here. Our acyl chloride comes in, bonds to the aluminum trichloride, makes this compound here. We then get that chlorine rips off that sigma bond electrons, making this compound with the positive charge on the carbon. Then we get a resonance form of this. Remember, more bonds, less energy. So even though it has a positive charge, it is still most favored, or the most major resonance contributor. Pi electrons from the aromatic compound reach out to that carbon and is going to attach as such. And then we get elimination, and we are left with our final product here. So, okay, I just wanted to make an important note here. We won't get rearrangements and we won't get polyalkylation as we saw in the friedel-craft alkylation. So the reason we don't get rearrangements is when we form this ion here. Remember that This is resonance stabilized carbocation, so no matter what it's in, we won't get any rearrangements because of the resonance here. And we call this the Acylation ion. Acylation ion gets a special name because it's so special. We love it, so we're going to actually give it a beautiful star here. Look at that beautiful star. So remember, Acylation ion, no rearrangements. No re. We'll just put no re ... Okay. Another thing that's important to point out is we're not going to get any polyalkylation, and that's because this is what we call a deactivating group. And again, we'll get into more detail when we get there, but I just want to point out that if we look at the resonance structures here, we'll see that we can get this one and this is pulling electron density away from the compound. We get this here. So we kind of have a dipole, an overall dipole. If I were to just draw on this molecule up here, if I were to draw like a big dipole, you'd see it's going that way. It's removing electron density from the ring. So it's already aromatic. The electrons are very low in energy. But if you add a withdrawing group, that's going to make it even worse. It's just like those electrons don't even want to react really. So remember that acyl group there makes it unreactive basically, and we're not going to get the polyalkylation that we saw previously. Thank you guys for watching this episode. Quite a long one this one was, but it's very important, very good tool in your arsenal of organic chemistry. Hope you enjoyed. Make sure to check out the other videos. We covered sulfonation, nitration, halogenation. We're going to go through some more niche reactions, and then we're going to get into the fun activating, deactivating groups. So thank you guys for watching. Have a wonderful day.